This is part 2 of calculating EQ, but today I'm going to show you guys how to use the temperatures and the change in temperatures to build bar charts. And in order to do that, we have to go over to the mathematical relationships and look at the ones that apply most to building the bar charts. So if I want to figure out how much EQ is stored in the water in state 1, I need to find out not the change in EQ, not the equilibrium transfers between like we did in the last problem, but I just need to use regular EQ to find out what the EQ is at some certain temperature at some moment in time. So we're going to have to do those calculations, but on these bar charts I want you guys to make sure you're putting your temperatures into Kelvin and not Celsius, since Celsius gives us issues whenever temperature is 0 or negative, and it makes it look like EQ can be 0 when it's really not, or negative EQ, which does not make sense right now conceptually to our class. So the first thing we need to do is go back to the problem and look at all the temperatures for the objects in our systems and change those into Kelvin by kind of cheating and just adding the 273. So I went ahead and wrote the final equilibrium temperature we got from the last problem. This is the temperature that the water and the gold get to after the gold has transferred its energy into the water, and they're both at the same current temperature at that moment. This is not the temperature after they cool back down to room temp. So if you read the prompts, state 1 is when the water is at room temp and the metal has been heated to 300 degrees Celsius. The second state is when the water and the metal are at equilibrium temperature. That's that 27.6 that we're going to turn into Kelvin also. The third state is when the water and metal are at room temperature. And I'm going to say that the room temperature is the 22 degrees Celsius. So the equilibrium temperature still has to decrease temp into the third state to get to 22 degrees. So you guys just got to do the scratch work. Again, I recommend you guys pause the video and try to get the essential pieces here on your own before just copying down my work. So I'm just going to do the temperatures off of the drawing I sketched over on the right. The temperature of the gold in the beginning is 300 degrees Celsius, but if we add 273 to the gold, as long as my calculations aren't wrong, you guys should end up with 573 Kelvin. And the initial water is at room temperature, let's assume. So that's 22 degrees Celsius. And if we add 273 to that water becomes 295 Kelvin. So now we've got the initial Kelvin of the gold, the initial Kelvin of the room temp water. So now we need to come down here and we can label kind of both the equilibrium temperatures, and then the final temperatures can kind of be calculated below. But at equilibrium, we said in the final problem that the water and the gold are at 27.6 degrees Celsius. So we're going to just calculate the 27.6 Celsius plus the 273. And when you guys do that, both the gold and the water are currently at 300.6 Kelvin. For the equilibrium. So I'm just going to abbreviate equilibrium. That's a U. But then you guys also got to think about third state. Once that energy transfers from the gold to the water and it gets to 300.6 Kelvin, the water and the gold eventually do cool down to room temp and transfer energy out to the surroundings. So I'm going to assume when they're at room temp, both the gold and the water is at 22 degrees. So this is state 3 here. This is state 2 information, and this is state 1 information up there. So 22 degrees Celsius, again, we've already done this in the previous problem. up here above when the water was at room temp, but we'll just do it again to show you. So the gold and the water are at 22 degrees in the third state. So 22 plus 273 should be 295 Kelvin. So now that we've got all the temperatures for every object in every system at every state, we can now go through and do the EQ equation. So technically what you guys have to do, you have to do an EQ equation and calculate for every state. So that's a total of 6 equations that you guys have to do. Again, if you're caught up at this point, you might want to pause the video and take this information and try to calculate the EQ for every state and every object in the system before moving on and listening to the video. I'm going to do the calculations for water, state 1, state 2, and state 3 back to back. I want to remind you, I'm stealing this relationship over here, mass times C times T. So EQ for the water, let's say state 1, I'll put a little 1 down the bottom so we know it's EQ state 1. The mass of the water was 150 grams. Times the specific heat capacity of 4.18 joules for every gram, and I'm going to say Kelvin this time since we're working in Kelvin, grams Kelvin. And the temperature at state 1 of the water we calculated to be 295 Kelvin. Now when you go to multiply this, you need to keep track of what units canceled for this to make sense. I know I'm trying to solve for EQ. That's an energy quantity. That means I need to end up with joules as a unit. So if you look carefully, the grams cancel, the grams on the specific heat. The Kelvin cancels, the Kelvin on the specific heat also. And we're only left with joules in the end. So if you guys multiply 150 times 4.18 times 295, and as long as I did this correctly, you should be looking at 184,965 joules in the water in state 1. Now let's just go on and do state 2. 150 grams again. This is a repeat. Got the specific heat capacity. But what's different now about state 2 is the temperature. The water has warmed up because the gold has been placed in it and transferred energy from the gold to the water. So that it's been an increase. And we calculated previously that the water and the gold at equilibrium are at 300.6 degrees Kelvin. If you carefully multiply across and cancel your units, the grams, the Kelvin, you should end up with 188,476.2 joules, but I'm just going to round to the 6 and leave it at 6. So that was pretty straightforward for it warming up. Now in the state 3, the water's back at room temp again. I'm not going to make anyone recalculate that because state 3 for the water is similar to state 1. Water was at room temp in state 1. So really, I'm just going to write down my answer so I can have it on my screen. State 3 is going to be the same as the 184,965 joules. Okay, that's water. Now water's done. Now we got to do the same thing for gold at each state and moment in time. So I'm going to do EQ for state 1. Now the mass for gold was 100 grams. The specific heat capacity for gold is only 0.13 joules for every gram Kelvin. And again, I'm using Kelvin because I'm requiring people on the bar charts to put it in Kelvin to avoid zero EQ and negative EQ calculations. The temperature of the gold in the initial state is when it's been heated. And the direction said it was to 300 Celsius. We calculated that in state 1 and we added 273 and we got 573. So I'm going to multiply it times 573 Kelvin. And we're back to basic practices here where we're going to cancel out the grams. The kelvins cancel out and we're only left with joules for a unit, and that's perfect because that's what EQ should be measured in. It's an energy reading, an energy quantity. If you and I carefully multiply across the top, 100 times the 0.13 times the 573, you guys should be looking at 7,449 joules. Now, if you already start to notice, the water's initial state, even when it's cooler, has 184,000 some joules. This only has 7,000 joules because the specific heat is so different than the water. Now let's continue on here to get the EQ at the second state when the gold and the water is at equilibrium. So we said before, the gold and the water equilibrium temperature, we calculated that previously at 27.6 degrees Celsius. We added 273 for state 2, and this one's going to be 300.6 degrees Kelvin. So I'm going to take the 100 grams again for the same gold sample, the same specific heat capacity for gold, and I'm going to take it times 300. 300.6 Kelvin. And we're doing the same process, canceling units that don't need to be around anymore and cancel through the act of division, essentially, with the grams in the numerator and the grams in the denominator of the units over here. Same thing with the Kelvin. If you and I carefully multiply across the top, you should find that the joules decrease because the gold has donated its water and transferred it, or excuse me, the gold has donated and transferred its energy to the water, so it's cooled down, and I got 3,907.8 joules. So there's a decrease from state 1 to state 2, which makes sense because you had a sample of hot gold placed into cool water and energy transfers from hot to cold, so you'd expect that to decrease. And then finally, EQ, state 3, same thing, 100 gram sample. Times the specific heat of gold. And then the temperature in the final is at room temp. Now the gold wasn't at room temp before, so I can't just steal the state 1 gold EQ because the gold is actually very hot in the beginning. So I have to do this as a separate calculation. And we previously decided that the room temp calculation was 22 degrees Celsius, add 273, and that should be 295 Kelvin. And if you and I calculate that out, we should get 3,835 joules. Now some of these joules of energy might not match up accurately once we plot them on the bar chart due to rounding in the previous problem, but also just currently here I may round some of these to make them easier to write. So be aware of that it may not work out perfect when we do our transfer arrows. Okay, so I know a strategy I've been recommending is that out of all these thermal energy joule calculations, you guys should identify which one's the largest and which one's the smallest. The largest one out of the bunch should be the 188,000 joules. Okay, so I'm just going to put a little star here. That's the largest, and you should look for the smallest one now. The smallest one is going to be the gold when it's at room temp. To me, that makes sense because gold had a very, very, very small specific heat capacity, and its mass is less than water, so I already know it's at room temp, so it should be the coolest it's going to be and the lowest EQ. So now I'm going to go and find the largest state, and I'm going to make it the largest bar on my graph. So I'm going to find state 2 of the water, and I'm just going to maximize as best I can the bar of energy for EQ. And this is going to be my 188,000. And when I write these out, I'm going to skip the decimals, and I'm just going to write to the ones place. There you go. Next, I'm going to go and do the smallest one. I want to do the largest and the smallest, so that gives me room to manipulate the bars for the rest of the joule calculations we did. Now, when I find the 3,835 joules, that's in the third state. Now, I've been showing people it's such a small number. I'm just going to put a line here that it mimics a very, very small bar, because if you kind of calculate through a ratio through division, 188,000 divided by the smallest 3,800 joules over here, this thing's like 50 times larger. We just can't scale it with only 10 lines on the y-axis here. So the best thing we do is just make general judgments and label it with the actual measurements. So I'm going to put 3,835 joules. EQ's the storage category. Now I can start to kind of fill in the other ones. And the water is kind of easy. The first state water is at 184,965 joules. You know, that I'm not going to proportion that out perfectly because of how large the difference is between the gold and the water. But I'm going to make sure I at least decrease it one amount so it communicates it's less visually on the graph, but then it also matches quantitatively with the values we calculated. And again, state 3 for the water is back at room temp, so I'm just going to do the same thing in state 3 because state 3 is the same condition as state 1. And I'm going to label my categories for the way energy is stored, and we're focusing on EQ. Now, conservation of energy says that energy can't just appear and disappear without any accounting for it and judging where it came from or where it transferred to. So the energy increased from state 1 to state 2. So we have to say, logically, the only thing responsible for warming up the water is probably the hot piece of gold. So we have to put a transfer arrow into the system circle from the gold. And the way you guys figure out how much energy, simply just subtract the second state from the first state to do the change in. And I'll do that quickly here on the side. So I'll try to write in red here so you guys can see. So let's do change in EQ. Now I'm not doing the change in EQ from the relationship up at the top of the screen necessarily. I'm just simply saying I've got an EQ in state 2, an EQ in state 1. I'm just going to simply subtract them. So I'm going to take 188,476 joules. And I'm going to subtract it from the initial, state 1, 184,965 joules. And when you do that, you should get approximately 3,511.2, but but I'm just going to roll with the 3,511. So we need to label that 3,511 joules in from the gold. Now I'm going to go ahead and do the second state to third state quite easily, because once the water decreases temp back to room temperature, that same amount of energy must be transferred out to the surroundings. Once the gold and the water get to the same temperature in state 2 and the water decreases back to room temp, it's got to have the same transfer out. Whatever energy the gold gave and donated just gets transferred out to the surroundings at this point. So I'm just going to abbreviate surroundings with SURR dot, and I'm going to do negative 3,511. And if you wanted to find out how you got that, you can simply take the last state, state 3, minus state 2, and it should give you a negative number of approximately 3,511, as long as rounding didn't interfere too much with that. Now we need to do the same thing for the change in for the gold, from state 1 to state 2. So let's build the bar charts first, and then we'll do the change-ins. So in state 1, we've got 7,449 joules. State 2 is a little bit less. So these are all slightly, state 1 and state 2 are slightly more than state 3, but yet they're tremendously less than the water's 180-some thousand. So I'm basically just going to start by increasing the second state just a little bit from the 38,000 or the 3,835 up to the 3,907, and I'm just going to basically bring that up to one full one. And normally I don't shade these in, but because they're so small, I'm going to shade them in. So that shows visually that it's more, but I actually might take that back a little bit so it's not so dramatic. And then label it with 3,907.8. We can fit that on there. And then in state 1, when the gold was as hot as it could be, it was actually up to about 7,000. So maybe 7,000 versus these two values down here, maybe I'll make it approximately double. It's not exactly that. 7,449 joules. This energy is stored as EQ. And now we can go and do the change-ins between them. So the gold decreased EQ because it gave energy to the water, because the water was cooler. So we're just going to subtract state 2 from state 1 to get the change in. So 3,907.8 joules minus the initial state 1. As long as these calculations are correct, we should see that the gold has a decrease of 3,541.2 joules. So that means that energy is transferred out to the water, and I want to label how much goes on there. Negative 3,541.2 joules, if you can fit it. And again, some of these values might not add up. The energy donated from the gold to the water in the problem above should be the same as the one below, but because of rounding and other issues from the previous calculation, these are slightly off, but they're reasonably close enough for now. All right, now the EQ transfer from state 2 to state 3, I just can't simply copy like I did for the water, because the gold is not in the same condition in state 3 as it was in state 1. In state 1 it was hot. State 3 it's room temp. But water in state 3 and state 1 was the same condition, so we just kind of stole that information. So I have to do one more EQ. This was water, and here we got gold. So I'm going to take the final state, 3,835 joules, minus the second state, 3,907.8 joules. And if you subtract those two, you should get the amount that's transferred out to the surroundings when the gold cools down just a little bit more. And if I did that accurately, I got approximately negative 72.8 joules of energy transferred out of the gold to the surroundings. 72.8 joules. And that's going out to the surroundings also, let's assume. In the end, it goes through the water and out to the surroundings. So please follow these guidelines when you guys are thinking about applying them to new problems, and come in and get help as needed.